Okay, I think we'll get started if everyone's ready. My name is Amy Bull. I'm on the faculty here at Penn State, and it's my great pleasure to introduce our next speaker, Oliver Einsle from University of Freiburg. Oliver trained with Peter Kronik and Doug Rees, and he's had his own group for about the past 10 years or a little more at University of Freiburg, and he's made many important contributions to understanding structure and function of metalloproteins and membrane proteins as well that are involved in the nitrogen cycle and in ion transport. And he's really kind of the perfect structural biologist, biochemist to participate in this workshop because he's also done really innovative work in method development at the interface between crystallography and spectroscopy. Many of you have already interacted with Oliver in the practical sessions, and if you have done that, then you know that he's really good at communicating how much fun it is to solve a protein crystal structure and learn what macromolecule that you're working on looks like for the first time. Please join me in welcoming Oliver. We're very lucky to have him here, and I'm sure he's set to give a really exciting lecture on the basics of protein crystallography.
Thank you very much, Amy, for this kind introduction, for the invitation. It's always great fun to be here. It's usually not so much fun to talk right after Frank, but at least I know that I can throw all the formulas I have at you, and you won't be very scared about that. In principle, I should call this talk structural biology because the thing we're doing is not necessarily just related to looking at crystals, but what we want is in principle a very simple task. It's way simpler than anything related to spectroscopy, I guess. In principle, we just want to see what we're working with, which is a very basic question that people are asking, and what that comes with is also, of course, that we are doing this very old-fashioned classical type of science in the sense that we are making discoveries and that we are seeing things that people haven't seen before without having to fly to different planets, although that would be quite cool. Well, technically, we want to do something like this. So technically, we want to do something like a simple microscopy experiment where you would have an object. I'm a biologist by training, so that's the kind of object I would be looking at. And you would shine light at it, and you would choose that light to be of the proper wavelength to be actually diffracted by that object. And then, of course, you could do all kinds of spectroscopies with that. That's probably what most of you would be doing. Or you put an imaging component behind it, and for optical light, that might be a lens, and that just leads you to a bigger picture of what you have. That's not very sophisticated, but it's basically something that is a very useful methodology to do as more or less the first experiment that you're doing, because we all agree that knowing the structure of a molecule is not all that you need to know about that molecule. But I would argue that ideally it's the first thing that you know about that molecule before you start doing anything else. And that's not only so that you know where the atoms are actually sitting, but it's also because in order to get to the structure of a molecule in the first place, you will need to make sure that you're able to make your sample at reasonable amounts and reasonable purity. And that's also kind of an important point for everything else you're doing with it. Now, of course, we're not looking at bacteria, but we want to look at molecules, and you all know what that means. It means that we have to adjust the wavelength that we use to the size of that part of the object that we would need to know. And if we say we want to do microscopy, then of course this would not be possible with light microscopy, even with super resolution light microscopy. That is very prominent these days, but it would well be possible with electron microscopy. And technically everything is in place, and the wavelength of an electron is easily enough to visualize individual atoms, which is actually done in material sciences. It's not done in life sciences because an electron is a particle with a mass, and if you shoot an electron beam at a biological sample, you visualize this very well because you easily burn holes into it. So the problem is that biological samples have produce very low contrast, and the electrons have very high masses and thereby impulses. So you get pictures with only a very limited resolution, which is why many people, including few crystallographers other than me, used to call electron microscopy on an atomic scale blobology, right? Because you would always get these kind of fuzzy little things. And that, as you probably all know, has changed significantly in recent years. If you look at Nature magazine, like 2 weeks ago or so, I think they had 3 full articles in there. All of them had a headline structural biology, and all of them were electron microscopy, cryo-EM high-resolution structures. And the main reason, actually, why that has happened is something I want to talk a bit later about. Because first, I wanted to mention why we actually care, because an important point that you also see from electron microscopy is, of course, if you don't reach a sufficiently high resolution with your system, you may still get quite an information on how a protein chain is going, how different subunits of a molecule interact, and that's all valuable information. But it's information that doesn't help us very much in bioinorganic chemistry, because we obviously care not only about mechanisms, and we don't only care about chemical questions, but we care about systems that are in many ways non-canonical, that are systems that you will not be able to describe based on a library, that are systems that people, in fact, haven't seen before. And this is just a few examples of recent years, which I think visualize this very well, starting with just this very recent story that Amy, together with Squire here, had in Science, which is on radical enzymes. It's an extremely fascinating class of molecules that's coming up. We already heard about oxygen-evolving complex. There was this recent ultra-high atomic resolution structure of nickel-iron hydrogenase that actually showed a hydride ion bound in here. There is also nitrogenase female cofactor. So this is all systems where you don't really know what to expect, right? You want to look at them, and you want to look at them at a level of detail that really tells you at least where every atom is placed in space exactly, or as exactly as possible. Okay, now why are we not doing this with electron microscopy? Well, if you look at an electron microscope, this is kind of the non-top fancy model, but it's something that very well shows the setup of how this works. This is really totally like a normal microscope. It has a light source, which in this case is an electron gun, and it has focusing optics because electrons have a negative charge, so you can use magnetic lenses to focus them. This is extremely important. And then you go through a specimen, and in order to limit the damage that these electrons do to the specimen, you cool everything to 100 K. You have an objective, and you have some further optics before you put everything onto a detector. And the reason that electron microscopy has made such a massive step forward in the last 5 years is due to this detector. And what has happened there has also happened in X-ray crystallography, because these CMOS sensor detectors have been developed that really changed the game for electron microscopy, and they did a lot to X-ray diffraction as well. Because what you can do with these detectors is you can directly count what's incoming, electrons or X-ray photons. So the old system was that you would basically have a detector for X-rays or electrons, where the electrons would hit either a scintillator in that case, or the X-rays would hit a fluorescent screen. They would cause a cascade of signal that would then, through a fiber optics taper, be transmitted to a CCD chip. And that limits what you can do with it, because this cascade that you generate in that first layer creates a certain point spread, which defocuses your image, necessarily due to the technology, because as a cascade you also need this as an additional amplification of your signal. And with the CMOS detectors, you're basically able to directly detect incoming photons or electrons on each individual pixel of the detector. You do not need to integrate, you do not wait over time, you just count what's coming in. These things look like that. They are pretty big and pretty expensive, so they're more something for larger research facilities than for your home lab. But they have changed the game for X-ray crystallography, and have afterwards led to a total change of what you can do with electron microscopy. So this is the method. This is the instrument of choice, the Titan Cryos. It has a pretty good name, and it's about 10 feet high, so it's quite an impressive machine. It's the same I showed you before, just with a fancy case around. That's what people learn from Apple, I guess. And this is what everybody uses really nowadays to get all these things that you have. And then, of course, the appropriate magazines go for it and will give you editorials and headlines in the idea that science is just still very held back, saying electron microscopes close to imaging individual atoms. Nature says the revolution will not be crystallized in new method sweeps through structural biology. That's where it starts to get personal. But anyway, and of course, Nature Methods, who has this as method of the year 2015, even speaks about the end of blobology. And that's, of course, really true. So it's extremely exciting what's happening at that point, especially because right now that the instruments come out, a lot of people have really interesting samples in their freezer that they never got crystallized so far. So they just put it in, and they get structures out. And you find things like 2.2 angstrom resolution structures, no, of basically beta-galactosidase in complex with an inhibitor. If you look at the electron microscopy reconstruction and even zoom in onto that, it looks a lot like what you know from a crystallography paper, right? Or it's these extremely big things like the trisnerp, which is a part of the spliceosome, 3.7 angstroms resolution, incredibly big thing, wonderful story. And you see RNA and protein in really sufficient detail to build atomic models. So this is really where those methods are coming together. And of course, they even say at 2.3 angstroms, you can start to look at drug targets and look at ligand binding to such drug targets. I'd be a bit cautious at that point, but even so, you do get these amazing results that totally wouldn't have been possible even 2 years ago. So calling this a revolution is definitely not an exaggeration. So why are we not all doing X-ray crystallography? One reason, of course, is that at this point, the instrument, why are we not all doing electron microscopy, of course? The instruments are slightly highly priced. So you, for what I showed you, the cryos, you would pay probably something like 5 to 6 million, plus an annual service contract. That's pretty much of a killer. So you could buy around 50 X-ray diffractometers for that. Nobody needs 50 X-ray diffractometers, but you get the picture. And the other point, of course, is that what you have in X-ray crystallography is that you are far from being stuck at 2 angstroms. So when it starts to get to molecular questions, of course, ideally, you want to start getting to resolutions that really show you positions of individual atoms. That's one thing. And it's going to be a way to go for electron microscopy to get there. And it's also that if X-ray crystallography actually works out, as you see in the practicals, where it takes us about an hour to solve a structure completely from scratch, it's a pretty well-established and fast method. So I guess the days are not quite over. Anyway, so it's all in all nothing else than electron microscopy. You still take your X-ray source, you still shoot those at your object, which in this case is a crystal, and I have to get back to that, and it gets the X-rays get diffracted on that crystal. The problems start at the point when you say, why don't we take a lens and image what we get as a diffraction pattern, because there are no imaging lenses for X-rays. It's light waves. You don't have a charge like for an electron microscope, and all you can do is basically look at what happens in the diffraction process and wonder what to do about it. And what happens in the diffraction process is something like this. So you will get pictures of this kind, which are arguably very beautiful, but it's not immediately apparent how the structure of your protein looks, right, once you look at that. So crystallography is a rather broad topic. And actually, Amy gave a lecture on this 2 years ago. Her slides are in the folder, and I think that lecture was way broader than what I'm going to talk about. So I'll pick a bit of a topic, and I leave some others out, maybe giving me the chance to be invited again to fill in some of the gaps. But in the end, really today, I would like to focus on what this is and what's actually happening here. So I would mainly talk about the idea of this diffraction image and what to do with it and what to learn from it. Okay, so everything started something like 100 and odd years ago with obviously the invention of X-rays. You need to have X-rays before you're even able to interrogate molecules on that level, and they were invented by this gentleman here, I guess with a hairdo that's fashionable again nowadays. This is Wilhelm Conrad Röntgen. He was working in Würzburg in Germany. This is his lab. Actually, it pretty much looks like most labs today. And he was experimenting on cathode ray tubes. Now, a cathode ray tube was a thing like this, where you basically would have a cathode that would shoot an electron beam at an anode, and if you would put enough voltage on this system, the electron beam would actually miss the anode due to the momentum of the electrons and hit the fluorescent screen here, where it would produce a light bulb. So this guy was not trying to invent a diffractometer or not trying to invent an X-ray machine. He was actually trying to invent the TV. Okay. Now what he found was that if he put a box over that thing, and that was even before Fox was on air, right? And he still put a box on it, he noticed that in many cases his second machine that was standing somewhere in the corner of a lab would all of a sudden discharge and show fluorescence, although this one was covered. I really don't know why he did that, but the point was that he realized that there must be something emitted from this system, from the fluorescent screen actually, that can transmit that cardboard, and from there on everything went quickly. He characterized those rays, and he actually called in his wife and told her to put her hand in that beam, and then realized that it actually passes through this very well. And this is where all this started, so that he then got the Nobel Prize in Physics, and it was actually the first Nobel Prize ever given. And that was a long history of Nobel Prizes. I will show you that one a couple of times over. It's not a trivial story, but it has actually had very wide implications in many aspects. Now, X-ray sources nowadays don't really look like that. You might find X-ray sources like that still for medical X-rays in some cases. What we are using are systems that, for example, especially for small molecule crystallography, look like that. So the whole tube is in here. You have a big focusing optics, and this is a cathode ray tube. It's a so-called sealed tube, and it produces a fixed wavelength X-ray radiation, and it's the method of choice for small molecule crystallography, where you have crystals that are really solid and that diffract really well. It's rather cheap. It basically has little maintenance. At some point it stops working, you throw it away, you get a new one. But of course it has a rather low intensity. So if your crystals are not perfect, which is usually the case in protein crystallography, you would like to have a bit more, like, photons per square millimeter. So the next bigger machine would be a rotating anode X-ray generator, which is still a cathode ray tube, but with a big anode that you cool from the inside with liquid, because this works at something like 50 kilovolts. And that rotates so that you don't actually burn a hole in it with the electron beam. The parts are replaceable. The whole machine is around 300K, and the maintenance is limited. So this is the kind of thing that you would use in your home lab. But of course, there are many reasons to go to higher intensities, either to get better data or, and that is something I will get back to, in order not to be limited to a single wavelength, because these guys only produce one single wavelength. And then you would have to go to synchrotron source. These are, of course, slightly bigger. So this is what, every group might have several of these. Every university might have one of those, and every country might have a few of these. And of course, the X-rays were usually a byproduct of particle physics. They didn't really use them. Nowadays, synchrotrons are built really for the generation of X-rays. And the brilliance, so the photon density, the photon flux you get from these kind of machines is many orders of magnitude higher than what you get from these kind of things. And it's as much as we need, because we usually already have to attenuate the beam in order not to fry our crystals in a very short time. So at a home source, a diffractometer could look something like this. Basically, this is a rotating anode generator. It produces X-rays to the right and to the left, so you can always put two detectors. It's a rather simple machine in the end. On a synchrotron, then, you have an electron beam that is generated in a linear accelerator, and then there is a so-called booster ring, which is a set of magnets that pulse in energy in order to accelerate these electrons to near light speed, and then get them into a so-called storage ring, where again you have magnets, and whenever these magnets are used to bend the beam to force it onto a circular path, a fan of X-rays will be emitted in this tangential direction, which is why all these experimental stations are always arranged like that. And then you have a beam coming out, you put a monochromator, you put an experimental station, and then you put a bit of lead, ideally, before the places where the experimenters are sitting and evaluating their data. And all synchrotrons are built like that nowadays. I just show you one, not because it's the best or the fanciest, but because it's probably the most nicely localized. This is the city of Grenoble in France, and I guess you all can see the synchrotron. It's actually here. and it's actually very scenic. So we hardly ever go there because we have a closer one, but it's probably the one that's most nicely located. And it's also one of the larger ones. It's about the size of APS with a circumference of the ring of 844 meters. This is a 6 giga-electron volt source with only 200 milliamps of current. So there is not many electrons going around. They're actually going around in bunches, but they have a whole lot of energy. And that's the idea behind. Now, the next bigger thing, because the bigger machines are always better, is then, of course, already in development. The first one is already working. So, of course, the Europeans wanted to build one. The Americans wanted to build one. So what the Americans did was they built one. The Europeans started discussing. So the American one has been working for a while. The European is just basically starting to be built. I show it anyway because I think it's way cool how they build it, because it's slightly going downhill, you know. So the actual source has to be built underground. It's this whole Resident Evil thing going on, you know. And the laser would be here, okay? And what happens is that you have a 3 kilometer or 3.5 kilometer laser that then is split at some point into individual experimental stations. And if you want, you can put matter in that path, and that matter will not be happy about it, but it will ideally tell you something about its structure before. And the way this works is quite amazing. That's why I like to show these things. So the idea is that X-rays are ionizing radiation. And lots of X-rays do a lot of ionization. So if you hit the sample with a free electron laser, this is a simulation, you will actually ionize this molecule to such a degree that there is so much of an overwhelming positive charge left that you get an explosion. It's called a Coulombic explosion. So the whole matter blows apart within something like 50 femtoseconds. Now, that's fun, but it doesn't tell you much, unless, of course, you build your laser in a way that your whole pulse length is only something like 2 to 5 femtoseconds. So before this starts exploding, the experiment is actually over. You get all your diffraction in a pulse at this point before the particle actually explodes. So you will not get the chance to shoot again, obviously, but you can collect your data at that point, and of course it gives you a theoretical time resolution in the femtosecond range, what you can do here. You get something like 5 times 10 to the 33 photons per square millimeter. That's a light source. Okay, and the things you can do with that are manifold. So one is, it's a laser. Yes, please, Ryan.
On your previous slide, how is this measured, or is this just a simulation?
That's a simulation.
Okay.
That's a simulation.
Then how do they know what the time scale of that will be?
Well, it is a calculation, and I guess they built the machine and found that it's more or less right. I wonder how good they are with these calculations. So but it's physicists, you know, you tell them you find the God particle and you get your collider. So it worked out anyway. Now what you can get, of course, is you get one image per sample that you put in. And the cool thing is that it's a laser, so the X-rays are coherent, and that means you can do imaging, which is what we cannot do. So this is a diffraction image of a single virus particle. They couldn't do much with it, but it kind of shows that you can collect data from individual objects. So can you do structural biology without crystals? Well, theoretically you can. And the other thing that they successfully did was to use nanocrystals, which is like 50 milliliters of nanocrystal solution, 50. They used photosystem because the people doing this in Phoenix, Arizona, are actually people who worked on photosystem before, and it's a very nice system. And they basically got data sets that show electron density for this by combining 10,000 diffraction images out of 3 million recorded images. So 3 million shots with a laser. And then you check if you by accident hit a crystal, and if that crystal diffracted, and then you try to extract diffraction data from that. So it's not exactly subtle, right? But it does work, and it's very much in development. And of course, it's something that one may want to keep an eye on. Now, anyway, that's not what we're doing. The diffraction data sets that you were looking at in the practicals, or will be looking at in the practicals, just have 180 images, and these images look somewhat like that. And what I want to really talk about from here on is basically how to get from the diffraction image to what we know as a structure. So these are the kind of things that we publish in papers. This is actually the one that we are solving in the practicals. And the non-trivial thing about this is that X-rays get diffracted by electrons. X-rays get diffracted by electrons. It's obvious, but what we deposit in databases is coordinates of atoms. So that is not the result of our experiment. Okay? The result of the experiment is, in fact, something like this. It's a distribution of electrons in space. And of course, you assume that the electrons look or hang around where the atoms are, right? And that's what's happening. But it tells you, for example, that it's not possible to directly determine elements by X-ray diffraction. All you can do is you can count, integrate the number of electrons, and estimate what element that might be. So we want to get to a three-dimensional structural model, and in order to do that, we basically have to build that model manually or in an automated way into an electron density map. But that's an interpretation. Every model that you're looking at is an interpretation of an electron density map, and the model per se has 3 decimals for each atomic coordinate, which is given in angstroms. That does not represent the precision of that structure. So you should go back to the paper and look at what it's actually worth, right? And this, again, comes from a diffraction image, and this diffraction image is related to the electron density map in principle through a Fourier transform. And I say in principle because there is a little more to it. Now, in order to do this, you shoot your X-rays at a crystal. And protein crystals are nothing spectacular. They are actually what you would imagine a crystal to look like. They are small, so they might be 100 microns to half a millimeter to a millimeter at most. But although they are built by proteins, which are very irregular objects, they have sharp edges, they have all the symmetries and all the niceness that you would expect from a crystal. So that's really what we're taking and what we're looking at. And the good thing is that it kind of looks like quite a challenge to convince your protein to crystallize in a way like that, but it's not necessarily like that. So I have this picture in which I would like to just brush over because that's the picture everybody always shows, so I put it in for your slides, and rather get you the thermodynamic version of this, which is basically something like this. So the idea is that monomers in solution require a substantial hydration shell. And if you want to get rid of this hydration shell to make these molecules aggregate in a more or less ordered fashion, then at first you have to invest some energy to do that, because the molecules by themselves are kind of okay the way they are. But if you get to a certain critical point where you have generated aggregates that just have a critical size, then it will be energetically favorable to add more to them, because the energy gain by shedding your hydration shell, or the entropy gain of the system by shedding your hydration shell, if you can form contacts on like 3 sides or so, is so much higher that at some point it goes by itself. And then the whole process becomes energetically favorable and crystals grow. So the message is, at that point, every protein wants to crystallize. Okay? Not every protein knows that. Might take some convincing, but it's not an exception, and it's not a miracle if these things crystallize. It's just thermodynamics. Okay? And we all like thermodynamics. I found this very nice illustration how to highlight the problems a bit, so I'm not going into any practical details of the crystallization. Just keep in mind that technically it should work. But of course, along the way, many things can go wrong, and this is a slide I stole from Alan Darcy from Novartis, and I think that's actually quite nicely illustrating what's happening. So crystallization will be hindered if your sample is not pure. Okay? If you have different types of proteins in there, in most cases, it's not going to work out. If these proteins stick together, if you get aggregation, it's not going to form crystals. If you have flexible domains, if you need to purify your protein with a GST tag or with as an MBP fusion that's linked via a flexible linker, it's usually not going to crystallize. If you have a flexible tail, it's usually not going to crystallize. It's not homogeneous. Go back to the lab, cut it off. If proteolysis occurs, many cases it's not going to crystallize unless you're able to isolate a stable fragment that then crystallizes even better than the whole thing. But in most cases, it's not a funny thing, and if your protein partially unfolds, it's pretty obvious. If you have pure protein, and pure means homogeneous protein, and that can be quite an issue. You can have protein that looks totally pure on a size exclusion chromatography. If you look at light scattering or something, you see that it's not monodisperse, and that might be a reason why it doesn't crystallize. But if you have pure protein, then most likely it will start to obey the laws of thermodynamics and form crystals, which would be something like this. No? So again, the main obstacle in structure solution nowadays, no matter what method you use, I would say is good protein biochemistry. So make sure that your sample is homogeneous, and that is something that can only be beneficial for whatever other technique you want to use on it. Okay, now what's a crystal? A crystal is basically a very simple object. A crystal is a translational repetition of a minimal unit. Again, it's a translational repetition. There is a unit cell, which is one of these small blocks, and that's just pushed around in space. Not rotated, not squeezed, not anything, just translated and infinitely translated. And this is what we call the crystal lattice. And this crystal lattice then on top might have internal symmetries within the unit cell. Okay? The unit cell forms the crystal lattice, which is a translational lattice. Everything that happens in terms of symmetry happens within the unit cell and can be described by assigning your crystal to one of 230 space groups. Okay. Nobody was really cheering when Frank started to talk about the pleasures of group theory, so I guess I also spare you that. But keep in mind that in principle there is internal symmetry in the unit cell. Now, what we are doing in crystallography is basically solving the structure of whatever is in the unit cell, which means that once we do that, we know the exact position of every atom in the unit cell, and the unit cell is just translationally repeated to form the entire crystal, which means we know the precise position of every single atom in the entire crystal. Okay. So these unit cells are parallel epipets. They are usually given as something like this. So the opposite sides are parallel, but all the angles, alpha, beta, and gamma, need not be 90 degrees. They can be somewhere off. And you have axes A, B, and C, and the angles, alpha is opposite to the A-axis, beta to the B-axis, gamma to the C-axis. You can calculate the volume of that, and you see that when the angles get 90 degrees and all this turns to zeros, the volume is just A times B times C. And these things then can have only a very limited set of classes. So we have crystal classes, and they get an additional element of centering, and that forms these bodies that we call the Bravais lattices. And that's all the positions that repetitive objects in space can take so that they fill space. There is only a square or trigonal, hexagonal face on the bottom. You cannot have anything with a 5-fold symmetry or a 7-fold or an 8-fold symmetry, because you will not be able to form space. So this is one of those, is the one that has to be chosen. And when you're in the practicals and you're initially indexing your data set, you actually get a list of these 14 Bravais lattices, and you have to choose one. And you choose one with the highest symmetry. And they have certain metric and symmetry restrictions down from triclinic, which means that any angle can be different and all the sides can be different as long as the opposing sides are parallel, up to cubic, where all angles are 90 degrees and all the sides have the same length. Okay. This is something that we need to assign. It's one of 230 space groups. Some of these space groups have symmetry elements that require chirality, that require that your molecule is racemic or not optically active. That is not the case for proteins. They are chiral, so you're left with only 65 space groups. And you need to identify that space group, because otherwise you will not succeed in describing what your crystal is made of. Okay. And then I skip all the part about symmetry, by just showing you this picture. It's actually very nice to use Maurits Escher's picture for all these symmetry ideas. He drew a lot of these repetitive two-dimensional patterns. And if you look at this kind of picture, it shows obviously the structure of a bird and a fish with wings. Ask me not. But that is really the structure that is encoded here, right? Okay? And if you go back here and you use this as your unit cell, then you will find that bird looking down here, you will find the fish looking up here, okay? And then you can start translating that, so it's again here, the fish looking up, the bird looking down, and so on. And then you go up here and you say, oops, wait, there is the fish looking down and the bird looking up. And you cannot get that by just translating your unit cell, which kind of means that this is not your unit cell. Okay? Your unit cell is in fact fish looking down, fish looking up, bird looking up, bird looking down. So this is your unit cell. Okay? And it contains that actual unit twice. Okay? And you don't care about two fishes and two birds. You want the structure of the fish-bird complex. And that would be that. And that is all you need to model, because you know that there is a twofold symmetry within your unit cell relating these guys. And that is the difference between what we call the unit cell and the asymmetric unit of the crystal. So the unit cell contains several asymmetric units that are related by crystal symmetry, and the unit cell is the repetitive element, while the asymmetric unit is what we have to put in our model. And this can very well be a pentamer or a heptamer, because the symmetry in here is not a crystal symmetry. That's why it's called an asymmetric unit. Okay, so this is the model we are after in the end. Okay, so we shoot X-rays at our crystals. Well, actually, electron microscopy works well without crystals. Why do we need crystals in the first place? That is not quite an unimportant question, because getting those crystals may be the main obstacle in your PhD thesis, right, for quite some. And the reason for that is that crystals are amplifiers, basically. Well, not like that, but a crystal is a repetition of like many points in space that are arranged in the same fashion. And you can already visualize this by this simple double slit experiment that everybody knows from freshman physics, where you get interference, something like that, between two point waves that are generated at a grid. And this is the same kind of point waves that we generate by elastic scattering of every point on such a lattice. And what happens here is that you generate minima and maxima. And you probably also know that if you take more slits, like if you go from a grid with a grading of 4, you get maxima like these. If you go to a grading of 8, you get maxima like that. What this picture doesn't show you is that the intensity of these maxima is much higher than down here, but you also see the spacing gets slightly larger, and everything in between here is cancelled out. This is because you get interference. And you get constructive interference if all your scattered waves are perfectly in phase, and you get destructive interference for every other point. So it's either all or nothing. Now, what is not interfering constructively will be cancelled out. And that is the reason why we see little black spots and not more. No. So the crystal amplifies the diffraction image, and it also makes it discrete. That's kind of a question. So do we lose information if we go to a discrete diffraction image? Because only very few spots on your detector actually show up. That's something we may want to address at some point. Okay, so crystals are amplifiers. We need crystals because we would not be able to detect anything. And that's where the free electron laser comes in. If you take enough photons, if you annihilate your particle really utterly, then maybe you can still get a bit of signal out. But this is not normally the case for us. Okay, so we get diffraction. You all know the idea. If you look at this general picture of a prism, you go in with white light, you come out with all these colors. And of course, what gets out of here depends on an intrinsic property of this object that causes the diffraction. In this case, it's the refractive index. But the process of diffraction encodes information about the object in the light that you shine on it in the diffracted waves. And in fact, and that's the great thing about it, it encodes all the information you need to reverse this process. So if you collect information about the diffracted waves, you can go backwards and reconstruct, figure out what properties of the object you had caused that kind of diffraction. And the process that takes you back and forth at that point is a Fourier transform. And this Fourier transform might seem a bit difficult, but in fact, it's what a lens does. So a stupid little piece of glass or plastic can do it. It shouldn't be too hard for us to do it, you would guess. Okay, this all started rather early. I'm just showing this picture. It's actually my only German slide, but this is quite untranslatable. So this gentleman is Max von Laue, and he went to a meeting of the Kaiser Wilhelm Society. The Kaiser Wilhelm Society was the predecessor of the Max Planck Society, where Frank is the director at this point. And at some point, the emperor got kind of out of fashion, so they thought, let's change the name. And they made Max Planck the first president of that society. And he said, well, why don't we call it Max Planck Society? And that's still the name today. And he just reports about a meeting in the year 1912, where Max von Laue, probably everybody was dressed up like that. You know, it must have been, I don't know, kind of nice, was coming and was showing his newest results. And he was actually shooting X-rays that had just been invented shortly before at a piece of zinc blende, so zinc sulfide, a crystal. And he was producing pictures that looked like that. And Max Planck then says that when he showed this picture that showed these regular distances, everybody, and they're very smart people, of course, everybody immediately understood what that meant, which is that information about that object is encoded in this kind of pattern. Everybody was going, ah. You know, imagine these old guys in the dark room going like, ah. Because everybody felt that a big deed had been done. And indeed, I guess that is kind of true. So we're back to these diffraction images. Now, what do they mean? If we look at a picture like that, what we get is several things. One is we get little black spots, and we call these black spots reflections. They are the maxima of constructive interference of the X-ray beam on the crystal lattice. As simple as that. No? So destructive interference cancels out everything except at one given point. Then what we also see from this picture is what the resolution of our structure is. Because in fact, points that are closer to the center correspond to lower resolution, while points or reflections that are further away from the center correspond to higher resolution. So if you look at a diffraction image, the one thing you want to see that is that it extends far out on that plate. And of course, this is again an image that goes all the way to the edge. Usually they get weaker and kind of fade out. Okay. Then we have these funny rings. That's something we have to talk about briefly. It's not so obvious why these rings show up here. The points are nicely in line, but it's also kind of round. Why is this round? Lunes, they're called. And finally, there is a white spot in the middle. And that's the so-called beam stop shadow, because most of the photons you shoot at your crystal, of course, don't get diffracted. And they would hit the detector and basically blacken the entire detector. So what you do is you put a little piece of lead in the way of the beam, and you catch the primary beam. You also catch all the forward scattering, which doesn't have structural information, but it could be useful to get absolute values for your electron density in the end. But we can't get that. So that's a diffraction image. Is that all? Well, it's not quite all. If you rotate your crystal, this is two diffraction images taken from the same crystal after a 1 degree rotation of that crystal. Would you say it's the same? It's not, no. You see that immediately. Very good. Because, I mean, if you look here, it's kind of the same. Now, this is the beam stop holder. This is the beam stop shadow. Here it's kind of the same. But if you look up there, it's actually quite different. So the positions change of these spots, and the intensities of the spots change. And that's an important point. So if you rotate your crystal, the diffraction image changes, which means, and this is now a series like a little movie, we can also, or we do look at this in the practicals, which means there is more to it than just one diffraction image. So this whole set of reflections is, of course, a three-dimensional lattice, because it is generated from diffraction on a three-dimensional crystal. Your Fourier representation is as three-dimensional as your real space object. But you need to rotate your crystal to move different reflections into diffraction condition. So what we need is not a diffraction image, but we need a data set of diffraction images. This can be 50 or 60 or 180 as in the practicals, or 10,000 as on the free electron laser, but it's always the same. And all the data we draw out of that is for each black spot, for each single black spot, we get an intensity value, and we need to put indices on this black spot. And they are integer indices. They're called the Miller indices. We call them H, K, and L. And they are just like the position in this whole diffraction lattice that we have here. So out of all these gigabytes and terabytes of graphic files that we get from our detector, the final result of data processing is just a little table, a little text file that for each black spot, and that's important, for each single black spot has one line, HKL, then F, or intensity, call it what you want, and the standard deviation for it. That's what we drag out of it. So we measure the intensities of every single black spot. We is the computer, of course, but in the first structures, this was done by hand. Not funny. Okay. Now, that's one of the more important slides, one of the few important slides, I don't know. What we get out of this is two things. One is the position of the diffraction maxima is what determines the numbers H, K, and L that we give to it. We just count. 0, 0, 0 is in the middle, and then the HKLs just go out as you count. And the position only depends on the metrics of the unit cell. Okay? It's only the dimensions of the unit cell that determines where we find the black spots. While everything that we want to know, which is the contents of the unit cell, is encoded in the intensities of these diffraction maxima. So we need to understand the metrics of the crystal, step one, and then we need to go, after understanding how this is built, and that means after understanding which reflections HKL or which indices HKL to assign, and then we just go and measure intensities, which means we fit a 2D Gaussian and integrate that. Okay, and that's why this process is called, well, the first step is called indexing, and the second step is called integration. So that's what we do there. Okay, and in the end, then, of course, we can look at this table and plot it, for example, like this. So this would be a plot of all these reflections, and we would call this the reciprocal lattice. We don't see this on one single diffraction image, but if we get everything collected and all the indices HKL assigned, then this is what we can reconstruct from it. And the Miller indices are just counting in 3 dimensions. HKL sticks out, just counting reflections, one after another. It's just basically the numbers. And it's called the reciprocal lattice because if you have large crystal axes, then the distances here are short. And if you have small crystal axes, then the distances are long. It's just an inverse relationship that comes from diffraction. I'll show you a few pictures on that. So another way to visualize this would be to say you just have this 3-dimensional table in principle, and you have spots that give you different HKL indices. You have the different axes of the reciprocal lattice, and you would have this spot at an HKL index of 2, 3, 0, and up there, then you would have 2, 3, 1, the way it goes up. So it's just really counting at that point, and the vector pointing from the origin of the reciprocal lattice to a given point in here is kind of a positional vector in Fourier space, which then obviously would have the components H, K, and L. We call this S, or the diffraction vector D star. Probably so that people could call one of the first programs to evaluate these things D Star Trek. Okay. The reciprocal lattice is built like this. So this is not 3-dimensional, it's a 2D picture. The reciprocal lattice has reciprocal dimensions. So A star, the reciprocal axis, has inverse length of A. It's kind of hard to show this in one picture, so it starts to be a bit imaginary. And it's orthogonal. If it's A star, it's orthogonal to the BC plane. So it's just inverse if it's an orthogonal cell, but if it's not, then it's a bit crooked. But it's rather simple to basically calculate. And of course, the dimensions of the reciprocal lattice, which brings me to the next point, are angstroms to the -1, 1 over angstroms, which means it doesn't exist in real space, which is not much of a problem. We have a lot of those, and we kind of ignore that. So the unit cell also doesn't exist, right? There are no points at the edges of a unit cell. It's just a concept. Your crystal is made up of protein. But these kind of virtual concepts help us a lot. Okay, now this is where we put our reflections, okay? This guy again. Question is, of course, if it's diffraction, why are we talking about reflections all the time? What is this? It's not a reflection. It's a diffraction process, and yet we speak about reflections. Okay. And that is because we have a super simple way of calculating where these reflections should be. This is not like I'm not pulling out any Hamilton operators. It's almost shamefully simple. But what it took was the concept of lattice planes. And that is something that's not so unfamiliar if you actually look at any kind of crystal lattice. No? You do that and you look at it and you think like, whoa, yeah, okay, that's some kind of a lattice. And if you look through, you see that no matter what way you look, there is always directions where the atoms line up very nicely. Here, and then you could also say here or here. So I'm living in an area where they grow a lot of wine. And if in winter you drive around there, you also see basically the sticks that they put the wine on, and you see the same thing. And if you drive by on a road and you look into something like this, if you ever do that, you will see that there is many positions where all of a sudden the sticks line up in many ways. And that's the idea of a lattice plane. You see them in a row, but there isn't really anything in there. But, and that's the funny part about it, if you act as if the X-ray beam was reflected on these lattice planes, then you find a super easy way to construct where a reflection maximum would show up, where a diffraction maximum would show up, constructive interference. So just to visualize this, let's say this is our vineyard or whatever we have. So this is in real space, axis A and B, a lattice that we're looking at. This lattice has a unit cell at some point, and then you can generate sets of lattice planes, as many as you want. You can, for example, say this is one type of lattice plane. It's always a set, they're always parallel, and they always go through all points in that lattice. And then you name them just by saying in how many parts they cut the edge of the unit cell. And this one obviously cuts the A-axis in one part and the B-axis in one part, and it goes down on B and up on A. So you would call this 1 minus 1. This set of lattice planes would get the indices H equals 1 and K equals minus 1. It's totally weird, right? What are we talking about here? Okay. Similarly, you could say this set of lattice planes cuts the A-axis in 2 and the B-axis in 1. So it's the set of lattice planes 2, 1. Miller indices H equals 2, K equals 1. That one, you probably get the picture. I don't ask you, but it cuts A in 2 parts, B in 3 parts. It's H equals 2, K equals 3. Okay? Now, nothing of this exists. Okay? But then, if you go on, and that was done by 2 gentlemen in the UK, William Bragg and William Bragg, father and son. And they thought, okay, now let's see what happens if we imagine that on such a set of lattice planes we get a reflection of our X-ray beam. Okay? Let's zoom in. So these lattice planes have a characteristic of D, a characteristic distance of D, and this is now reflection, which means the incident angle is the same as the outgoing angle. It's an angle theta, and of course we're coming in with a parallel wavefront. We have a right angle here because of the distance of lattice planes. We have a right angle here at the end of the wavefront, and we have a right angle here at the beginning of the wavefront, which means this theta again shows up at this point. Now, we get constructive interference from something like this if the path difference between those 2 waves here, that's the path difference, x, and that's actually easily calculated. It's basically, so x half, this part, is related to the hypotenuse D here, sine theta. So sine theta here will be this divided by that. Okay? And That's our path difference, and we get constructive interference if that is an integer multiple of the wavelength of our radiation. Now that is pretty simple. So constructive interference on n equals lambda. You put those two together, Bragg's law. N times lambda is 2d sine theta. Nobel Prize. Pretty cool, huh? No Hamilton operators, nothing, no integration. But the point is, of course, that this allows you, in fact, to completely relate reflections that you put on a detector to a certain set of lattice planes that come with their own HKL indices. And this is exactly the sorting scheme you need in the end to make the Fourier transform work. And that's all the mathematics you really need for it. Those are the two gentlemen. It's not John Cleese. And they were really some of the founders of crystallography as a science, because from then on it became possible really to work with these kind of things. And from there, just a very quick excursion. Now we can think what's actually happening with this whole diffraction process, because another gentleman came by, Paul Ewald, and thought of a way to visualize what's really happening with Bragg's law. And I'm doing this again in 2 dimensions, so everything I show you as numbers, of course, is vectors in space, but that doesn't make it much more complicated. 2 dimensions, it's actually very simple. So if we want to visualize Bragg's law, then he said, well, what's happening? We have a crystal, okay? And that crystal is hit by an X-ray beam. And, of course, this X-ray beam will be diffracted, but what we see is an outgoing beam that looks like it was reflected on some set of lattice planes. And he said, okay, now let's say we look at the direction of the beam, and we draw a circle around the crystal, okay, with a radius of 1 over lambda. Okay, the crystal is in real space. You can't draw anything with a radius of 1 over lambda because that's 1 over angstroms in dimensions. It's all virtual. Okay, it all doesn't exist. Okay, close your eyes, breathe. Still. And then he said, okay, then the origin of the reciprocal lattice would be at this point, and we're talking about Bragg's law. So in order for this to be fulfilled, of course, you get a diffraction maximum if Bragg's law is fulfilled, and we can check if that's the case. So if this is a reflection, then this reflection must come from this set of lattice planes so that you have this angle theta going in and coming out, which also kind of means that this angle is 2 theta. Okay? If you look at small molecule structures, 2 theta is how they tell you their resolution. You get a 2 theta angle. It's that one. Okay, so that means, again, that this here is basically fulfilling a diffraction condition if Bragg's law is fulfilled, and that is the case if this d star or d star half actually over lambda fits in here. And that is always the case if this 1 over lambda is fulfilled. So whatever spot is here on the surface of this sphere, or circle as I draw it, will be in diffraction condition. Well, this is the origin of the reciprocal lattice, which means the whole reciprocal lattice hangs around somewhere. And in the same space, in the angstrom to the -1 space that I'm drawing my sphere, I can also draw my reciprocal lattice. And that then would be somewhere here. And my reciprocal lattice with the axis HKL is somehow intersected by Ewald's sphere. And Bragg's law is only fulfilled if a spot is on the surface of this sphere. And that means, in this picture, only these reciprocal lattice points would actually give rise to diffraction spots on the detector. And that is why we get these strange patterns. Because if now we rotate the crystal, we rotate the reciprocal lattice with the crystal. And what's happening is basically this. So this is rotating, and you see that different spots intersect with the sphere. So at every position of the crystal, you will get a different pattern, which comes from different points in the reciprocal lattice. And if, of course, you have one here and one down there, then in 3 dimensions, these guys will form a ring. That's where these loons come from. And that's why you have these round features on the diffraction pattern, because it's technically an intersection of a sphere that is defined by your diffraction condition with this regular lattice that you have. You can turn a bit further like that, and you see that by rotating the crystal, you can probe the entire reciprocal lattice. That's how you get your data, and that's what a data set is all about. So that's kind of the idea here. And Bragg's law is also used to define the resolution of a crystal structure. If you see a structural paper, you usually see a resolution given as a D minimum, which is this here, and that's defined by that. So protein crystallographers would tell you a D minimum, while small molecule crystallographers would tell you a theta max, the diffraction angle, and that D minimum just means it's the set of lattice planes with the lowest spacing. The closer they are together, the higher is the resolution you get from that point, because the further you go away from the center, the higher those numbers get. And I told you the further you go away from the center, the higher is your resolution. And so we just give this minimal Bragg spacing between lattice planes as a resolution of our structure. And that's kind of convenient because it more or less fits to the definition of light microscopy, where you can say if you can distinguish 2 points, then that's the resolution you have. So you do need a resolution below 1.5 angstroms to get individual maxima for 2 carbons in a CC bond. But the definition of it is really that, and it means it's the reflections, the furthest out, the HKL, defined by the HKL indices, that we actually record. So that's the idea behind the diffraction, and it also tells you that it's not too hard to understand. So you get comfortable with these kind of things, even to the point that you say it's a reciprocal lattice, okay? So you see many spots that are close together here, which means reciprocal. In that direction, your crystal must have a long axis. Closely spaced spots means long axis, and vice versa. And you can even say, okay, the crystal must lie in there somewhere like that, which sometimes is useful if you need to consider what you do with it. Okay. That's how we collect the data. So every individual black spot, every reflection represents a scattered wave amplified by constructive interference. Okay. And what we can do there, if we have all of these, is that we just go and we Fourier transform this. And the really amazing thing about the Fourier transform is that we have a term here, which is the term of what we just have collected. I'll say a bit more about this in a moment. And that is a discrete term. We only have diffraction information for HKL as integer values for only given points in space. And yet, after the Fourier transform, we can calculate electron density at every point XYZ in space. This is discrete, this is continuous, and that works. And this is the formula. It's actually the only formula we ever need to get us from the diffraction image to the electron density map. Okay. Now, the Fourier transform is a pretty neat thing. And if you look at what it does, it's actually kind of instructive to see what's happening in a diffraction process. Now, if you have one single atom, and you Fourier transform that atom, this has the shape of a Gaussian, and this still has the shape of a Gaussian. Goes forward and backward, that is all pretty much the same. The atom is a bit fuzzy, and the Gaussian is also a bit fuzzy. That's what it is. If you start to look at a molecule, and you Fourier transform this, then you get some kind of a pattern that totally does not look like the molecule, but it obviously has some structure. The colors encode phase information. Okay, I'll say a bit more about that in a moment. Okay, and again, the information contained in here is all you need to inverse that transform and go back to the picture of the molecule. That's what we're doing. Now we're having crystals. Okay, if you take this, and this is real Fourier transforms of these graphic files. Okay, that's really how this looks technically if you do this. If this is our crystal lattice, then this is our reciprocal lattice. Okay, I took focused points now, point atoms, in order not to wash this out so that it's better visible. And you see, if you have a distance here that's long, then you have a very closed spacing here. That's the reciprocity of the lattice. Okay, and the axis is not exactly collinear with that one, because this axis is orthogonal to that. That was the rule for constructing this. It's all pretty understandable. And if you build up, and now it gets interesting, if you build up your lattice from molecules, then you get something like that. And then you are at a diffraction image. And if you go back to the single molecule, of course, then you see that all the information on the structure is still in there. That's why this works. What you don't see on this picture is that due to the fact that you have a lattice here, this is millionfold amplified to the point to make it detectable. That's why we're doing this. Okay. Now, constructive interference means that each one of these spots actually represents a wave function. Okay? So I have to tell you a few words about how we see wave functions. Frank also mentioned wave functions already, and we're actually doing pretty much the same. But in principle, we're at least one step simpler because we have one problem less. Well, probably we have many problems less than theoreticians have, but concerning waves, we have one parameter less. Let's put it that way. So we're looking at a wave. Okay? Ideally, we have an intensity that varies over time, something like that. So this could be a simple cosine wave, and we can describe that by 3 parameters only, which is a wavelength. That's this. It is an amplitude. That's here. And it's a phase angle that kind of shifts the whole thing back and forward. Okay? That's all we need to describe such a wave. Now, what we do for various reasons is that we're using monochromatic X-rays. And that is extremely helpful because it means that whatever we have has the same wavelength. We're looking at elastic scattering. Elastic scattering does not change amplitudes. Elastic scattering does not, well, actually it changes the phase angle by 180 degrees, but that's not much of a problem. But it does not change the energy. It does not change the wavelength that we have. So everything we send onto our crystal and everything that comes out of our crystal has the same wavelength, which means we can ignore the wavelength. Okay? And that means we get to a simple description like that. So a simple cosine function that has 2 parameters, an amplitude, we call this absolute value of f, I'll tell you why in a moment, and a phase angle. Okay, good. Now, the way we describe waves is also something that Frank has shown, that all of you have seen a million times. We have this alteration of an electric and a magnetic vector, right? And that's why we describe all this as a complex function. Now, wait a minute, how did that work? If we use complex numbers, we are moving away from the real axis in number space, and we are moving into what's called the Gaussian plane. And this picture of a Gaussian plane is called an Argand diagram. So a complex number here would be represented by a value z, which has a real and an imaginary component, a and b. Okay? And of course, you can also represent it by its positional vector f, which then would have a length of absolute value of f, and it would have a phase angle of phi here. And then the real component would be f cosine phi, and the imaginary component would be absolute value f sine phi. Okay, that's how this goes, and that's what you all know, and that's how we describe waves. But where is the wave in there? Where is the periodicity of that function? Well, the periodicity of that function is basically on the third axis that we're not looking at. So the time axis, where this rotates, is coming out of the board at this point. And what you have to imagine then is that you get your wave by this vector rotating. And if you project this vector on the real and the imaginary axis, then you see that basically these two functions, this is your periodicity that you have. Okay? And this is what our waves do, and this is a complex exponential as figured out by Leonhard Euler, Swiss mathematician. Looks quite Swiss to me anyway. Who came up with this wonderful relationship showing that in complex space the exponential function is periodic. And so all the waves that we have in our diffraction experiment do this. Okay, that's kind of complicated. And all we need to do for our Fourier transform is to add up all the waves. And now the really great thing that makes our life so much easier is that all these waves have the same wavelength, which means they rotate at the same speed. Okay? The wavelength is the speed of rotation here. They all rotate at the same speed, which means we can just go and stop this picture. Okay? So whenever we add waves, we can do that at any point. We take one reference, and the position of all the other waves in the system, all the other reflections, all the other contributions of atoms, whatever we add here, are always the same. And that is why we used to represent waves by these simple vectors. And these vectors are called structure factors, and that's our Fourier representation of the structure. And it's a wave. because it would have theoretically a third axis where it rotates, but that doesn't tell us anything because everything rotates at the same speed. So this is the data we measure, and the little arrow represents a wave, and each wave represents one black spot on a diffraction image. And what we do on the diffraction image is we measure the intensity of the black spot, and the intensity is, with a few corrections, just the square of the structure factor amplitude. So we directly measure the structure factor amplitude. Okay? Very convenient. However, there is a little problem, because what we measure is not the structure factor amplitude, but we measure its square. So technically, we measure the square of a complex number, and the square of a complex number is the product of the complex number and its complex conjugate, which happens to be a real number. No? That's what we measure. And that real number is great because it easily allows us to go back to the amplitude, but per se, it loses all information about the phase angle. There are many ways how you can explain this, but bottom line is we cannot measure phase angles. We couldn't, even if our devices would allow us, because we're not using coherent X-rays at that point, so we don't know the phase angles of this whole stuff to start with. And of course, they're not coordinated upon diffraction. So we can measure amplitudes, but we cannot measure phase angles, period. This is the phase problem of crystallography. And what I keep telling in the practicals is that if you ever heard crystallography from a small molecule person, they probably never told you about the phase problem, right? And that is because for small molecules, the phase problem is solved, but for proteins, it's not. So for us, this is serious. We have this equation, which is an equation of limited complexity, and all we need to fill in is amplitudes here that we get directly from the diffraction experiment. This is the Fourier term that relates the two representations in real space and reciprocal space. And that is our phase angle, and we cannot measure our phase angle. Okay. That's not good. However, we do solve structures once in a while, so there must be a way around that, right? So see it positive. Question is, how is this phase information obtained? Well, okay. For small molecules, the problem is solved. And the problem is solved for small molecules because of these two gentlemen, Jerome Karl and Herbert Hauptmann, which I have to abuse a bit now, because this is the pictures I found, and I was always too lazy to make my own. They got the Nobel Prize for Chemistry in 1985 for solving the phase problem for small molecules. So if you go to a small molecule diffractometer, it's really that kind of thing like in CIS where you what we heard about the mass spectrometry. You basically push a button and the molecule pops up. There it really does. And that's because things can automate it if they are not too complicated, if the structures are not too big. Okay. Unfortunately, this does not help us too much. However, there is a certain use for those two gentlemen, because what I have actually is real space representations of their phases. Okay? I have two-dimensional phase densities of Karl and Hauptmann here. So what I can do with those, of course, is I can Fourier transform them. Okay? So I can basically generate a set of amplitudes, fjk, and a set of phase angles, phi jk, and a set of amplitudes here, fha, and a set of phase angles, phi hh. Okay. And then, of course, you can start messing up with them. That's great. And you can, for example, take the amplitudes of Jerome Karl and the phases of Herbert Hauptmann, and vice versa. And then you can back transform this, and you can see what happens. And you would probably guess that you end up with pretty much of a mess, right? That's what you would expect, because, I mean, after all, they are not that homologous. Okay? What you get is this. Okay? We cannot measure the phase angles. That's a real pity. But what's even worse is that the phase angles contain the bulk of structural information. So, I mean, it's all a bit washy, but you clearly recognize the source of the phase, not the source of the amplitudes. Okay? Electron microscopy is better in that. They can determine the phase better than the amplitude for different reasons, but for us, this problem is a real problem. Okay. So what we need is quite obvious. We need a way to determine phases, something like a phasor or so. So we're still working on that. There is actually already a program called phasor. I'm quite confident that this is going to work out, because when I saw this in the 80s, everybody also already had an iPad, and I have one by now. Just hope that they don't build it as a weapon. So, phase calculations are possible, and there are two general ways of doing this. One is kind of the easy way, and that is that you just say, well, okay, it's not like we're solving the first structure ever here, so there may be structures out there that look reasonably similar to what we have. Maybe because what we're just trying to look at is just a point mutant of a protein that we have already solved half a year before. And then you can, in fact, go and calculate phase angles from a known structure and combine them with the amplitudes of your own structure and calculate an electron density map there. Okay? That works. It's called molecular replacement. I'll say a few words about it in a moment. Problem is obvious. The bulk of the structural information is in the phases. So if you take your phases from another molecule, you have to be very careful that your structure doesn't just look like the other molecule. That's not what you want. Okay? And the better way, of course, is to say you do a de novo structure solution. And that you can either do by direct methods. This is what Karl and Hauptmann invented. And this is actually what, with a little trick, we are doing in the practicals. Well, actually, no. It's just what we use as a tool to go to the other point, which is called substructure analysis. So if your problem is too big to solve it, you need to find a way to go and make your problem smaller. It's that easy. And that means we start out by looking only at a subset of our structure that is so simple that we can solve it, and then take that information to go back to our real structure. Okay, a few words on molecular replacement. So the idea is simple. You have data from your unknown structure, and you could only measure the amplitudes. But you have a similar structure, and from that you can calculate amplitudes and phase angles. And then you use the phase angles from that structure combined with your amplitudes to generate an electron density map. Simple, but of course it crucially depends on the other molecule being similar, very similar, highly similar, and phase angles and amplitudes change with orientation of the molecule in the unit cell. So you need to take that model and place it in the unit cell of your new crystals in exactly the same position as your unknown molecule is positioned. Otherwise, you cannot compare these things. So it's kind of a shifting around of things in there. And the question is, of course, how you do that. And you do that by using, by actually going back to the electron density function. So this is what you would like to calculate, but you cannot calculate it because you don't have phase angles, right? So a gentleman called Arthur Patterson went along and said, well, then let's see what we can do. And if you actually, there are many ways of explaining this, but if, for example, you square this function, and you square the amplitudes, then you lose the phase angles here. It's again the complex function that if you square it, you fall back on the real axis. You lose the sine term, and you go back to a cosine, and you get a function that looks kind of similar, but that is not a Fourier transform anymore. But now, what does that function give you? Well, this Patterson function opens up a new type of space that we call Patterson space. Okay? And in this Patterson space, we do not have maxima that correspond to atom positions like in the electron density map, but we have maxima that correspond to interatomic distance vectors. Imagine real space. You have a structure of limited complexity, let's say 3 atoms. Okay? And these 3 atoms have positional vectors in real space. That's what you see in an electron density map. You do not see that in a Patterson map. In a Patterson map, you get vectors between these atoms only. And they have no relative position. They all come from the origin. So what you get is a Patterson map, UV space. No, it's an angstrom space. It's a real space, but it's not a space that gives you real atom positions, where you basically place all these vectors going in both directions. That vector would be here and here. That vector would be here and here. And that vector would be here and here. So the Patterson map would generate n squared peaks. N of those fall in the origin. They are peaks from each atom to itself. And the others are there. That's what you can calculate, while that you cannot calculate. Does it help you? Well, it does help you if the structure is simple enough, because the picture of your molecule is in there. And if you do it right, you can also actually derive positions of atoms from here. So that does work quite well. So the Petersen function is a good tool to solve simple structures. It does work if you have something like 100 atoms, and it's something that can be done not so badly. Okay. Now, if the substructure is simple enough, you can derive it from a Petersen map, and as you might guess, that's not the case for proteins. Okay. But if we manage to limit the complexity of our protein to something small enough to solve, for example, by that way, then we know a structure of a few atoms. Not so great, huh? We want to have the structure of the entire protein, not just of a few atoms. But the cool thing is that if we do that, it can actually help us, and I'll show you why. So imagine argon diagram, and now it comes to these vectors. So you get a vector for any of your reflections. And this is a vector for your protein with, let's say, a given heavy atom. You work with a metalloprotein, your protein might have an iron atom or something. And this vector is the simple vector sum of all individual diffraction contributions of all the atoms. So you might as well take that apart into the contribution from all the non-metal atoms and all the heavy atoms here. And just write it as this kind of simple vector sum. Okay? And these heavy atoms, let's say you have 3, 4, 5 irons in there, that would be simple enough. So if there is a way to find those few irons, then of course we could calculate their positions, and if we have their positions, we could determine both the phase angle and the amplitude for each reflection, because Fourier transforms work both ways. It's not really what we want, actually, because in principle what we want is FP. We want to have, or FPH, so we want to have one of those that we cannot determine easily. But the trick is now the following. This so-called phase triangle must be true for every reflection. And you get this information while you don't get those two. So what you can do, rather simply, is you just see what you have. Well, you want to get FP. Okay, so the absolute value of FP, which is, you want to get FP, but you do only have its absolute value, which means you have a vector here that has this length that is known, and it has just some phase angle. So it falls somewhere on that circle. Okay? Then, that's the FP circle. Then we have FH, and for that we know amplitude and phase, which means we can actually draw a vector. And then we have FPH, and again, we do not know the phase angle, but we know the amplitude. So we have this sum, which means that basically we might as well draw this vector up here. And again, we have this ambiguity here that the phase angle is unknown, but we know that all three together give you this phase triangle, and that phase triangle is actually only fulfilled where those two circles intersect. So only here and here we would actually fulfill this phase triangle, which means that the unknown phase for FP, which we are looking for, must be essentially one of these two. Okay? And that we can calculate for every single reflection, just by knowing the small structure of the heavy, the substructure of the heavy atoms. That's actually quite nice. We still have an ambiguity here, two possible solutions for each reflection. That is too much in order to just guess. But if we have a second heavy atom, for example, or another source of information like anomalous scattering that I talk about in a second, that ambiguity is lifted and we can calculate phase angles. And out of that, you have these moments when you push your button and the electron density pops up, like you go to your practicals. Because once you have everything together, the Fourier transform is a rather simple process. Okay. And just to close this up, finally, the methods that I'm also not going into detail about, there is two ways of getting these substructures. And one of them, that's kind of the brute force approach, is to say, well, you know, there are no substructures in there. I can't use 10,000 carbons. That's too many. So I just take some heavy atoms and throw them on top. That's called isomorphous replacement. And if you locate those few heavy atoms, then you can solve your structure. Alternatively, if you are smart enough at the beginning of your PhD to choose to work on metalloproteins, then of course you usually end up with having just a few atoms of a certain type in your system. And they are ideally suited to actually serve as this substructure, and you can even use effects like anomalous dispersion, I'm not going into that much, to just locate these individual positions. That's what we do in the practicals, and you can do this in one single data set, and you only find the irons first, and using a construction like these Harker circles, you get simple Patterson maps like that, no? And using a construction like the Harker circles, you can derive where your atoms are. No? So this is the Patterson map for the ferridoxin that we are solving in the practical, and you see there are peaks that even give you a hint how an iron-sulfur cluster looks like. You even get some signal for the sulfurs. So this is where that thing is. So this is the kind of information that we need to get substructures that then solve our real structures. And then the Fourier transform is calculated, and the magic happens, and you end up with something like this. And just to keep in mind, now this is an electron density map, and this is really the end of it. This is the result of the experiment. That's what we want to do, and this is what we have to interpret. But keep in mind that a ball like this that you see in here, or that's a single water molecule. We don't see the proton, so it's in fact it's an oxygen atom. And we see this directly at angstrom or sub-angstrom resolution. So we have the atomic microscopy that we're actually trying to get. And from here on, it's just interpretation. And if we get to that point with one of the electron densities, we kind of feel like we're in paradise. This is Hawaii. I just want to use this to illustrate what an electron density map really is, because in fact, if you look at this Fourier transform of a diffraction image of Hawaii, then one way to represent it, of course, and is maybe not such a beautiful way, but one that you find very often on maps is something like this, because you have your island, which has a certain height above sea level, so it's a three-dimensional object that you have in a two-dimensional representation, and in order to visualize this, you use contour lines. Okay? And just to clarify, what we have in the electron density map is just one contour line of a function of x, y, and z in three-dimensional space. And we can play with these contour lines, but that's the kind of maps we're looking at. And of course, in the old days, before there were computers, just to finish, we would have, or not we, but our forefathers would have two-dimensional models like this, plotted out, and then maybe plotted on transparent foils and stacked together, and they would look in and see how that molecule might look like, and then they had to build a model. And the first protein model that was ever built was built by John Kendrew, and it was the model of myoglobin, and it's a true piece of art. It looks like myoglobin, actually. It's a bit weathered, I guess. It's in the Science Museum in Cambridge, and that's really how he built it the first time, and probably people told him what they think it looks like, because he actually went back to start doing this a bit more elaborately and came up with that. But the first models that people had were physical models of these things. No? So that's kind of the thing. And just as a very last slide, when you look at structures, don't forget that the model is an interpretation. You get PDB files from the PDB that give you atomic coordinates for each atom with 3 digits. Okay? That's thousandths of an angstrom. We cannot determine that. And that's what every theoretician and too many spectroscopists put in their programs. Okay? Be cautious. If you plot this, it looks something like this, but don't just download the coordinates. Look at the paper. Look at quality indicators that should be in certain ranges, and we are usually pretty cautious about such things. But don't only trust the models, because the result of the experiment is the electron density map. Okay, and with that, I'd like to finish. I'd leave you with a few pieces of selected reading, and I thank you for your attention.
Thank you, Oliver. Time for a question or two. I actually have a question. It's okay. So in a lot of metalloprotein structures, if you look at certain forms of the electron density map, you'll sometimes see these ripples of negative electron density around the metals. And I think this is something that we even see in one of the data sets in the practical.
Yeah.
Can you comment a little bit on why
Well,
we see?
So what you get is, of course, that's a typical feature of all kinds of Fourier transforms. You also get this in Fourier transforms of spectra. And in principle, the Fourier transform reproduces a perfect representation of your object if you integrate over all of space. It's kind of an infinite integration, right? If you sum, in our case, an infinite number of structure factors. But we don't have that, of course. So what you get is the typical thing of series termination artifacts in the sense that you see the underlying repetitive structure of the wave that you are adding up. And you have a big contrast, like a heavy scatterer in close proximity to something lighter, then of course you get periodic artifacts around that. And that's hard to avoid, but you can predict it and you can take it into account. Okay.
I have a question. So you emphasized that the model that gets published and gets pretty pictures and so forth is an interpretation, and the electron density is the experimental data.
Yes.
But to what extent is the electron density also an interpretation because of ambiguities in solving the phase problem? So for example, if you have a metalloprotein with a couple of heavy atoms and you solve using MAD, to what extent will slight crystal defects and just protein-to-protein variation in the position of those atoms result in slight anomalies in the electron density that might not be physical?
Okay, that's actually a brilliant question because it raises 2 points that I didn't even mention so far. So the first is, like high-resolution electron microscopy, crystallography is an averaging technique. So all the little differences within a crystal already automatically manifest within the density you see, because that is always an average over all unit cells. So that's already in there, and that's part of your model. And we model this, for example, by having a refinement value that's called the B factor. It's a Debye-Waller factor, which is an atomic displacement that you take into account. And that kind of represents fuzziness of electron density. So the quality at that point is really, really decisive. And the other point I didn't kind of mention in detail is that the phase angles we have in the end on a refined model are not the ones that we determined in the experiment anymore, but they are the ones that we take from our model. Okay? So if you start going the wrong way at the beginning of your structure solution, you can really get some bias in, you can really do some mistakes, and there was a very unfair paper a couple of years ago where they kind of showed that there is an inverse relationship between structure quality and impact factor of the paper, of the journal that it's published in. And of course, if you go to those very high impact journals where people publish things that, unless they're metalloproteins, because they're so difficult and not many are working on, so we are good. But if you look at all this membrane stuff and whatever comes in there, of course, there is 5 other labs on the same structure. So you publish the first electron density you get out there, and that is, of course, you have to be careful. So the bias of phases that come from an incorrect model can be substantial, and it's much worse if your resolution is not very good.
We should stop there and move on to our next speaker. Let's thank Oliver again for a great talk.